EDSAC stands for Electronic Delay Storage Automatic Calculator. That's because EDSAC used something called delay lines for its memory. These were long tanks filled with mercury. Bits travelled through them as sound waves and were recirculated until they were needed. The mercury tubes were held in boxes called coffins. But mercury is expensive and mercury delay lines are unreliable and difficult to use. So for our replica, we're using nickel delay lines like this, which hide inside our coffins. In a nickel delay line, data travels as pulses from a transmitter along a coil of wire to a receiver at the other end.
Work on the main storage of EDSAC has progressed considerably, and we are now entering into a production phase. We have already completed the short delay lines that form the register banks of the machine, and are now looking at the main storage that contains program and data. This is one of the storage boxes. Each box contains 2 spiral wires capable of holding 576 bits or 72 bytes. The section in the middle here contains the 2 nickel spirals, and the stuff around the outside is necessary electronics that converts from the pulse forms used in mercury, which is what the rest of the machine is expecting to see from the pulse forms for metal delay lines. The signal from the main part of the EDSAC comes to a transducer unit with a pair of coils actuating a pair of nickel tapes. When a coil is placed around a nickel tape, it produces what are called longitudinal pulses, sound waves in the nickel running along its length. At the end of the tapes, we have a weld at which the tapes are welded to either side of a long length of a nickel steel alloy wire, and that induces a torsional or twisting mode pulse into the wire. These torsional pulses travel slightly slower and more reproducibly than the longitudinal ones. There is also a signal that goes this way, which is absorbed by a buffer here. The pulse goes round the spiral and travels along here and goes round this circle 3 times and comes out here, where it comes to another pair of tapes welded onto the far end of the wire. The signal now passes on these 2 tapes to another pair of transducer coils here. The signal from these coils is very small, and it's fed into a preamplifier in this screened box before being led off to further electronics over the back of the unit. The reason for the additional electronics is to ensure that the signals sent and received from this box are exactly as would be expected from the mercury delay lines in the original machine. So coming in here, we have a demodulator which feeds a signal up to a pulse shaper and driver that drives this coil, and then the signal from the preamplifier comes to a pulse shaper that restores the shape and length of the pulses, and then feeds the resulting signal into a modulator from which the RF pulses in their original form go back to the main part of the machine. So all this additional stuff is about converting pulse formats and restoring pulse lengths to the form it would have been if we had had a mercury delay line. Starting at the lower left of this schematic image, the radio frequency pulse comes in from the main part of the machine. This is then demodulated and reshaped for driving the delay line transducer. The ultrasonic pulse passes around the delay spiral and is received in a differential form. Further reshaping results in a rectangular pulse, which is then used to drive a modulator. The resulting radio frequency pulse returns to the main machine. And in the setup here, we have a unit we're going to test and a chassis 01, which is the chassis in EDSAC, which is responsible for interfacing with the store and regenerating the pulsed trains in storage. Testing the short delay lines was quite simple. We see here a display of one storage cycle on an oscilloscope screen, showing at the top the data entering in yellow, and below that leaving the delay in blue. We just need to check that they're the same. For the long lines, however, there are many more pulses and more potential echo sources to cause errors. Data received from the delay is more degraded, so an automatic approach using a continuously varying random pattern is needed. Only a small part of a storage cycle is seen here on the scope, and even if we were to zoom out to see it all, it would be hard to spot individual errors, and so statistical techniques must be used to estimate the error rate. The enclosures for the store units were made for us by a company in Cambridge. We have here a set of 10 of the unit boxes as delivered, and one which we've started to populate. You can see the front panel here, and if I look at this unit, which is got some of the internal workings, you can see sockets have been added. Over here, little spacers which will hold the printed circuit boards, grommets to protect the wire runs where they pass through screening partitions. And the next stage would be to add the supports for the delay line wires. There are 8 mounting points around the circle. Once the mechanical fit out is complete, the next stage is to add the printed circuit boards and then to provide the wiring harness connecting them together. The job of producing the printed circuit boards themselves has been farmed out to various of the volunteers on the project. In total there are about 250 boards to be produced, and so far we've produced a little over half of them. These units should be interchangeable. They are all built to the same specification, and if properly adjusted should be plug replaceable. Production is going on at a steady rate. Most of the additional electronics here is pretty basic stuff and quite easy to design and fabricate. There are problems with radio frequency interference and noise that mean we have to be very careful about things like screening and earthing, but it's a pretty well understood area. The main technical challenges are around the nickel wire delay line itself. So we've had to solve problems of fabricating the transducers, producing the welded mode transformers, and managing echoes and spurious signals within the wire itself. So this is a transducer. In operation, it slides along a pair of brass rails so that the length of the line can be adjusted, thereby adjusting the total delay. Each transducer has a small 2-pin plug for connecting it, and then 2 short stubs of thick instrument wire which act as mounting posts, and the 2 coils are here, and it's the fabrication of this unit that we're going to look at next. We're going to mount the coils onto little tabs of acetate sheet for ease of handling. So the first stage is to take one of these tabs and put holes in it which correspond to the positions that the tapes are going to have eventually. The coils in the transducer are wound onto wire formers, and here are a number of I've prepared previously, and on each one I have put a little piece of the insulation from standard instrument wire to act as an end stop. In preparation, we take the tab that we prepared and we run this wire. This is a 22 standard gauge wire, so it's 0.7 diameter, and that will form the hole through which the tapes pass. Put 2 wires in like that and run them in until we have just about 1 millimetre of clearance, which is where the coil is going to go. The tapes are going to run where these pieces of wire are. Right, we now need to apply a coil to these 2 wire formers, and to ensure that the coil is mechanically strong and wear resistant, we do this as a wet process into quick drying epoxy. So we mix this up, and from this point we have 5 minutes to complete the process. And then take just a dab of this, apply it around the gap where we want to put the coils, and then we take a wire that's been threaded through a piece of PTFE tube, and then we go the other way like that. Like that. And then we secure the tails with a small piece of tape to protect them. And then we go back and we cover the support pins up to the middle of the spacers, and we leave that to dry. Okay, the epoxy is now dried, and we can remove the pins that have acted as our former. And this tab now comes off, and we've got 2 coils embedded in epoxy on the plastic tab. And what we want to do is mount those onto their printed carrier, which we put on this pair of brass rails just for convenience of handling. So, taking a little more of the epoxy, and we can take this, positioning the wires so they come out in the direction we want to have them for soldering. And this needs to be perpendicular to the direction of the rails, so we use this little spring jig to hold it in place, and we now let that set. Now that the glue is set, we can remove the clamps, and we're nearly ready for the final stage. So we take the wires coming from the coils and put them round the connecting wires, like so. We just put a dab of solder on there. And the final stage is to test the unit, which I do by plugging an ohmmeter into the socket, and that gives me a reading of 3.6 ohms, which is about what I expect for these units, so that one's fine. We have now reached a stage in assembling the unit that we have the long delay line wire in place and need to install the nickel tapes that couple the wire to the transducer and then terminate in the buffer that suppresses the echoes. This involves us preparing some annealed tape and then fixing one length at a time, one below this wire and one above. And the fixing is done with a spot welding arrangement. The nickel tapes need to be rolled from round wire. The first stage is to take a nickel wire and pass a current through it to anneal it. This softens it to make it easier to roll. The next thing we do is take the wire that we've done the preliminary annealing on and use this rolling mill that Burton fabricated and pull the wire smoothly through the rollers, which flattens it to form a tape. But it's been again work hardened to a certain extent in that process, so we put it back into the clips and apply the current to re-anneal it. Now, the spot welder is a capacity discharge welder, so there's this little box over here that contains just a big capacitor and some relays and timing circuits. Before we can do the welding, we need to remove any oxide left over from the annealing process. So to do this, we place the tape carefully against a piece of scrap fiberboard, and with a piece of emery paper gently abrade the oxide layer, being very careful not to kink the tape, always taking strokes away. Now we're going to install the tape into the unit. And the first stage of this is to feed the tape through one of the coils. There we are, like so. So it needs to be running across the damping buffer, through the transducer, and up to the end of the wire here. To make the weld, we need to position a welding electrode. This is the bottom electrode, which is a copper anvil, on a shaped former so that it clips over to convenient bolts to keep it from moving about. So we put that in place, running under the wire. We then tuck the tape underneath, and then we put a positioning collar on, and then gently position the tape exactly at the end of the wire. And then we take the second welding electrode and apply it like that. Apply a steady pressure, and okay, so that tape is now attached. So we now repeat the process with the second tape. And we take the tape and feed it through the second coil, positioning it again at the end of the wire. Take the second electrode right on top there and weld. And the final stage is to close up the buffer unit here. The tapes have to pass between multiple layers, so that at the bottom we have some hard black neoprene, and then these are rubber foam, which we bend back so that we zigzag the tapes through this unit. It turns out that the attenuation has to be very gradual, because otherwise you get an echo at the beginning of the unit. And it's important that the tapes don't actually touch within the body of the unit, or again there'll be an echo from that. And an upper neoprene layer. And then we put the top plate on. All the stages of assembly use little special tools or jigs for positioning things, and this is quite a lot of the effort of the project has gone into getting these just right to do their job. And the final thing is to earth the tapes, as otherwise there's radio frequency pickup that gets into the preamplifier. So now we've installed one pair of tapes and its associated buffer, and the next thing to do is test it. So we put on the other end and we run pulses through it. This in general won't produce a satisfactory result first time. If the pulses are irregular, one possible cause is that these tapes are overlapping very slightly from the wire, and to deal with that we have to file off the ends of the tape like this until there's a very clean termination of the tapes at the point of the weld. We then had to remove any residual echoes by adjusting the pressure at the different faces of the echo buffer here, which we do by adjusting these nuts. Our experience so far has been that once adjusted and suitably filed, the setup is stable, and we can then do the final adjustment for timing on the chassis 1, adjusting using worst case data patterns until we get error-free running. And our idea of error-free running is if a unit runs for 20 minutes without any single bit error, then it's okay for testing in the real machine. We're now at Bletchley Park, standing in front of the EDSAC replica. And I'm standing next to one of the coffins that contains the delay lines. So inside this box, we have 16 tanks worth of nickel delay line. Sitting on top of the box, we have a replica of the kind of mercury delay that would have been in the tank originally. And you can see here that there is a long steel tube that was filled with mercury. And at either end, there's a transducer sending and receiving data. And these would have been in contact with the mercury inside the tube. This little stub here is for filling them with mercury, which is quite a delicate process. The easiest way to demonstrate that the store is working is to load program into it. We can do that with the initial orders unit. This unit contains a small piece of program just sufficient to get things started and to read further paper tapes, and that program is hardwired on the back of a bank of uniselectors here. When those unit selectors are activated, the data is fed into the store and can then be used later for executing the program. This is the interfacing rack that contains electronics for linking to the store and address decoding logic. Data comes in from the main part of the machine and is distributed between the various tanks that are within the scope of this rack. This is the operator's desk, and from here we can monitor various of the main functions of the machine on a series of cathode ray tubes. In particular, this one in the middle allows us to access different parts of the store. By changing these controls, we can select which of the tanks of the machine we are monitoring. Now let's make the whole process happen. As the initial orders load, we see them appearing on the screen here, starting at the bottom and running upwards. When the first tank is full, loading switches to the second tank, and we can follow that process by adjusting this knob, which selects the next tank. So we've shown that the long delay lines work, and this is a significant milestone for the project.